Physics part 397, we continue the section questions and we continue with our question number 2, 2D. The energy available from the complete fission of 1.00 G of uranium 235. So we say calculate the energy available from the complete fission of 1.00 gram of uranium 235. Calculate the mass of uranium-235 used by a 500 megawatt nuclear power station in 1 hour, assuming 30% efficiency. Question number 3. Two fusion reactions which take place in the Sun are described below. E. Hydrogen 2 deuterium nucleus absorbs a proton to form a helium-3 nucleus. 3b. Two helium-3 nuclei fuse to form a helium-4 nucleus plus two free protons. For each reaction, write down the appropriate nuclear equation, calculate the energy released. Section 13.12, Probing Matter. At the end of section 13.12, you should be able to infer from the results of alpha particles scattering experiment the existence and small size of nucleus. Well, the figure shows a photograph taken with an ion microscope, a device which makes the use of Broglie wavelength of gas ions. It shows a sample of iridium at a magnification of about 5 million. The position of individual iridium atoms can be seen. Photographs like this reinforce the idea that all matter is made of very small particles. We call them atoms. Advances in science at the end of the 19th and the beginning of 20th century led most physicists to believe that atoms themselves are made of even smaller particles, some of which have positive charges or negative charges. Unfortunately, even the most powerful microscopes cannot show us the internal structure of the atoms. Many theories were put up about the structure of atoms, but it was a series of experiments carried out by Ernest Rutherford and his colleagues around 1910 that led to the birth of the model we now know as nuclear atom. We can't see it, but we just imagine it. And our imagination puts all the idea here as we see it around. Probing matter using alpha particle. In 1911, Rutherford and two of his associates, Giger and Marsden, fired a beam of alpha particle at a very thin piece of gold foil. A zinc sulfide detector was moved around the foil to see the direction in which alpha particles traveled after striking the foil. They discovered, number one, the vast majority of the alpha particles passed through the foil with very little or no deviation from their original path. They found, number two, a small number of particles were deviated through an angle of more than 10 degrees. They found, number three, an extremely small number of particles, 1/10,000, were deflected through an angle greater than 90 degrees. From these observations, following conclusions could be drawn. Number one, the majority of mass of an atom is concentrated in a very small volume at the center of the atom. Most alpha particles would therefore pass through the foil undeviated. The center or nucleus of an atom is positively charged. Alpha particles, which are also positively charged, passing close to the nucleus will experience a repulsive force causing them to deviate. Number three, only alpha particles